Welcome. In this video lesson, we are going to introduce the notion of a line integral, which is actually very fundamental in applications like physics. So before we get started with the line integral, let's motivate this by looking at an application in physics called work. So work is a measure of how much energy is exerted in order to complete a task, for example. It's the product of force and distance. Now, force is usually measured in something like newtons. And distance is usually measured in something like meters. So when we multiply the two together, we get units called Newton meters, often written as N-M, which is equal, 1 Newton meter is equal to what we call 1 joule. And 1 joule is just a form of energy. And so the reason it sort of makes sense to multiply these two things together is I can apply a 10 Newton force, for example, but it depends on for what distance I apply that force. So we can all probably agree that 10 newtons of force carried along 5 meters will end up exerting less energy than, say, 10 newtons of force for 20 meters. So it's kind of a sensible measurement because it does take into account both the size of the force and how long in terms of distance that force needs to be applied for. So in this case, we could see that the amount of work for a 10 Newton force across 5 meters would be 10 times 5, or 50 Newton meters, which we would just call 50 joules. The same thing could hold if you're talking about a force that's two-dimensional. This was a one-dimensional force. We sort of assumed that you had some sort of box here, and you applied a force against it to move it a total of 10 meters, or 5 meters, excuse me. So 5 meters would be here. This is the total distance we went across, and that force itself was a force of 10 newtons. But in this case, down here, we have a force. Both of the components are in newtons, but this force is two-dimensional. So in this two-dimensional force, we have the force vector 5, 10, which is, we'll just say this is 5 and this is 10 up here. So here's our force vector. And that force is going to be carried along a total of this distance, which, if you think about this as being the east-west, and this as being the north-south, then this 5 newtons is for every meter we move east, and this is the number of meters we move east. So if we want to know the total work, well, we're going to have to take the 5 newtons and multiply it by the 2 meters that we move in that direction. Now, we were moving along a diagonal, but keep in mind that if you're pushing a box at a diagonal, you have two components. You're actually pushing it east and you're pushing it north at the same time. So to that, we have to add the amount of work that was generated by moving the 10 newtons of force, or applying the 10 newtons of force for a total of 4 meters. And so we can see that's 10 newton meters plus 40 newton meters, which is 50 newton meters, which is the same thing as just saying 50 joules for short. So what is significant about this is that you can see it's a product and a sum, which would be the same thing as us taking the dot product between the 5, 10 vector and the 2, 4 vector. So the scalar is equal to the dot product between F times D. So the total amount of work is the dot product of the force multiplied by dotted with the distance vector. Now, in terms of the type of works, in some cases, if you were to, let's say, move in the opposite direction, suppose this were along some sort of incline that had an east-west and a north-south component to it, and you were pushing a box up that hill. So you're doing all the work. But if you were moving the opposite direction, then you would actually be, the actual incline would be doing the work for you, or gravity would be doing the work for you. So you could just place the box here at the top, and you could just let it slide down. And in that case, you would sort of be accumulating work, meaning that you're actually you have an excess of energy. I don't know if that's completely accurate in the physics sense, but that's sort of my interpretation of it. Obviously, it would be easier to allow that box to slide down the hill than for you to have to push it up. for it to slide down, it's not going to require any work at all. You're going to let gravity do all the effect. So there are two types of works that we'll actually consider. Before we get into that, let's go back for a moment and think about how the sine and cosine functions actually, or rather how the cosine function looks over the first 90 degrees. One of the things we established early on in our study of vectors is that the dot product between two vectors, and this is the law of cosine, the dot product between two vectors is equal to the product of their magnitudes times the cosine of the angle between those two vectors. So if this is u and v, then the angle between them, theta, connects the relationship between those vectors. One thing that we do know is that these magnitudes will always be positive. Now the dot product on this left-hand side could be zero, they could be positive, or it could be negative. So if theta, well, let's draw, if this is the theta axis and this is cosine of theta, I'll break this up into 4 intervals here. Not even 4 intervals, I'll just break this up into 2 intervals actually, because if you think about it, if two vectors are 180 degrees, if they've been rotated that far apart, then any slight rotation beyond that, we measure the smaller of the two angles. So 180 degrees is as far as we need to go. So here's 90 degrees, here's 180 degrees. And here is -1, here is +1. So cosine looks like this. Cosine starts at 1, drops to 0 at 90, becomes -1 at 180 degrees. So that means that if theta is between 0 and 90, which is between the y-axis and 90 degrees, we see that here cosine of theta is always positive. So if theta is between 0 and 90 degrees, all 3 of these terms on the right-hand side will be positive, and therefore the dot product will also be positive. However, if we look at the dot product when theta is 90 degrees, then we can see that the magnitude of u, provided that u and v are not zero vectors, the magnitude of u times the magnitude of v will produce a positive number. But now, because theta is 90 degrees, cosine of 90 degrees is 0, and so we have a positive times 0, and therefore the dot product will be 0. So if you compute the dot product and that number is bigger than 0, or it's a positive number, you know that the angle between them is somewhere between 0 and 90 degrees. If you compute the dot product and you obtain 0, then that means theta is 90 degrees. And finally, if the dot product is less than 0, well, that must mean that cosine of theta is negative, and that occurs between 90 degrees and 180 degrees. So here these two are still positive, but if theta is between 90 and 180 degrees, then this whole outcome will be negative, and that means that the angle between them is somewhere between 90 and 180. So just as an example, let's pick two vectors that we can easily identify. Let's say we have the 1, 0 vector, and we have some vector in here like the 1, 1 vector. If we compute the dot product, first of all, because this is on the x-axis and this lies in the first quadrant, if we dot these two vectors together, it should come as no surprise that we get a positive number. Now if we take two vectors that are perpendicular, like the 1, 0 and 0, 1 vector, we know that those are perpendicular. If we compute their dot product, not surprisingly, we get 1 times 0 plus 0 times 1, which is equal to 0. And as a final example, let's say that we have a vector that we know, this one here is 1, 0, and let's say we have one over here at -1, 1. So this angle is clearly more than 90 degrees, it's between 90 and 180, and if we compute the dot product between our two vectors, well, we get -1 in this particular example. So this process does work, and it enables us to think about where the two vectors are relative to one another. Now let's think for a moment about what this would mean if I had, let's say, a vector field. So imagine that I have a vector field here and I have a series of vectors, and I'll just keep this pretty simple to say they all kind of point that way. This is maybe a gradient vector field for a plane, and as we move in the direction of the vectors, we ascend to higher contours. So imagine that you're actually wanting to move in some direction relative to those vectors. So suppose that I wanted to actually move this way. That is, I wanted to travel against the current. We would call this C, and C just stands for the curve, the oriented curve that you are going to travel along. Okay, so this is some oriented curve. And you're going to travel against the flow, which we have talked about in the previous lesson. You're going to travel against the flow. And so if at any instant you compare your travel vector, if you break this oriented curve up into smaller, tiny vectors, and at every single point you compare that to the vector in the vector field, then you can see that those two vectors are exactly 180 degrees. Well, if I compute the dot product between my green vector, where I'm going, and the current vector, the red one, then what we're going to obtain is a dot product, which is, well, let's see, if theta is greater than 90 but less than or equal to 180 degrees, we're going to get a negative dot product. And if we repeat that, if we now basically break this whole curve up into a series of vectors always pointing along the path that we're taking, then we see that at every single point where we're going relative to the flow of current is 180 degrees. And we're going to obtain a bunch of negative dot products at any point along our oriented curve. And then if we sum up all of the dot products, and I'm going to write it like this. Our vector field, which is, remember, a vector field is a function where you input a position and it outputs the vector on that field. So all of those little pink vectors are generated by this function. And if I dot that with my position vector, that is, my position vector is these green vectors. So here we'll say, that's the red vector. These are the green vectors. If we sum all of those dot products together, well, we see that we're going to get, well, this one was negative, so we have a negative plus another negative plus some other negative dot product. And if we sum all these up, then we're going to get, in net, we're going to get a negative sum of dot products. What that tells me is that in overall, or in net, and in this case, at every single point, I was always going exactly opposite to the flow of current. This means that I am basically doing negative work. If you think about these as some sort of force or velocity vectors and my position is opposite those, that means that I have to do all the work, right? Because you're swimming upstream, as opposed to another example where maybe if we took this oriented curve, well, then our dot product between our position at any point, so let's say our trajectory starts here, there's my first position vector, r of t, and then, well, where does that current flow? At that point, it's in the exact same direction. Therefore, I am going to get 0 dot products, and that means that in net, I am going with the current the entire time. I'm going to get a dot product of 0. And then, of course, I could take trajectories that are kind of a little bit with and maybe a little bit against, and maybe that's what I want to do. I want to row my boat that way. So I'll ride the current for a little bit, and then I'll kind of be perpendicular to the current, but then I'll start going against the current. So this is actually what a line integral measures. A line integral is a measurement that represents the extent to which an oriented curve, C, goes with the vector field F or against it. That is, are we doing work? Is there no work being done? Is the phenomena causing the vector field doing the work? In other words, where is the work happening? So what we're going to do is we imagine that we are in some vector field, and this is the curve that we want to take. So this is our oriented curve C. And you can see that the arrow on here tells us that we're going to travel from the point P to the point Q. Now that curve itself is great, but we need to work with vectors. So what we're going to do to that curve is we're going to break it up. We're going to put a bunch of points here that are equally spaced on that curve, And between any two adjacent points, we're going to draw a vector. So you can see that, that the displacement vector, delta r, now we have to say the change in your position vector. For example, the change in position from this point here to this point here, we're going to call that change in delta r naught, and that is going to equal where your position is at time 1, or at location interval 1, minus where you are at position 0. So for example, let's just say that you were at you ended up at the point 3, 2, and you came from the point 1, 1. If you subtract these, that means in the x direction you traveled 2 units, in the y direction you traveled 1 unit, and so this is your displacement vector, how far you traveled in both components. We don't need to worry too much about all these indices, but we're saying like the delta r1 to get this vector here that we're calling delta r1, we subtract r2 minus r1, and that's going to give us the displacement vector between those 2 points. So if we break all these up, we're going to have a bunch of delta ri's. Okay, so that means we're going to have a bunch of these displacement vectors. But at each position, not only do we have our delta ri, which is the vector that just connects the dots like this, but we also have these blue vectors, and those are generated by the force. That is the vector field vector, or the force vector, or the velocity vector of the stream that we're going across. And so what we need to compute is, for example, if I wanted to know, well, here you can see the blue vector and the black vector kind of go in the same direction. That angle between them is really small. But if I wanted to say, am I going with or against the current? I could say, well, compute f, the velocity vector at the point r naught, dot that with the displacement vector, delta r naught, and that's going to give us a measure of to what extent we're going with or against the current at the initial point. But then in order to figure out the extent to which we're going with or against the current along the hole-oriented curve, you see that the angle is constantly changing between where the current is going and where we're going. You can see that that angle starts to kind of get large and then small again. Because of the fact that we're not going with the flow, we're kind of choosing our own path. So we would need to add to that the velocity at r1, which is this point here, that's that blue vector, multiplied by the displacement vector at that point, which is this guy here, delta r naught. And we're going to need to sum all of these together until we get to the last one here, which we're calling f at the last position, dotted with the displacement at the last position. And you can see that a simpler way of writing that is just to say that this equals the sum across all delta ri, that is across all of these little intervals here from this point to this point, and this point to this point, and this point to this point, all the way around until we compute the dot product for that last delta ri. And what's this going to be? Well, it's going to be the velocity at the current ri dotted with the change in position at that ri. And this is just adding a bunch of dot products together, just like we were thinking about up here, except now we're doing this for a curve where the vectors, the position vectors, keep changing. You can see that here the vector points kind of more upwards, but by the time you get here, your position vector is almost horizontal. And so we can't just compute one dot product, because not only is our position vector changing directions, but also our velocity vectors or force vectors could be changing directions at all. Now, of course, we're not satisfied with this, because no matter how small these intervals are, this is not going to be a very precise measurement. Until we make these points infinitesimally close together. So you guessed it, we're going to be computing a, we've already addressed this question here. Whenever we are summing things together, we want to, of course, be able to take an approximation and make it exact by saying, well, let's make delta Ri really tiny. So make delta Ri really, really, really small. Well, how do you do that? Well, you do that by, instead of having just these black points that we have along this curve, you put points in between the points, and you basically make infinitely many intervals, infinitely many tiny delta R vectors along this oriented curve. And so as you do that, instead of this being, in other words, taking the limit as delta Ri approaches 0, this is going to be the integral over that entire curve. We're just going to write it like that for now instead of putting boundaries, because these boundaries are going to vary from problem to problem. The vector field doesn't change. That's still going to be f of r. We don't need the subscripts anymore because this is at a point now. And whenever we make delta infinitesimally small, we call it d, and we call it dr. So what we have here is a dot product between two vectors, one that will contain some sort of force components, and the other one, dr, well, that's the change in your position. And you have two changes in your position. You have one that's in the x direction and one that's in the y direction. So if we think about this vector right here as being the dr vector, and then this, of course, will have two components in it, and that's going to vary from problem to problem what the vector field function is. As I dot those together, I am going to be able to compute the exact amount of work along that curvature. So this may look really convoluted, but this basically just embodies what we described up here. That if we take the integral over our entire curve of the dot products, that is what we get if we take the limit as the size of delta Ri, right? We said make delta Ri really, really small. We can't say delta Ri approaches 0, but we can say that the size of delta Ri approaches 0. And so that's just this messy notation here, the sum of all the dot products. You don't really need to worry too much about this because we're going to be computing it with an integral. Great. So how do we actually use this formula? Well, let's say that we want to find the integral of the constant vector field. So you can see that all these vectors are the vectors 1, 2, 1 unit in the x, 2 units in the y. And we want to take a straight path from 1, 1 to 10, 1, and then from 10, 1 to 10, 10. So we'll call that first segment C1. We call that second segment C2. So we know that in order to compute this integral, this is going to be the integral of the dot product between our force vector, or our vector field function, evaluated at our position, dotted with dr. Now as we begin to unpack this, f of r, that's just this vector here. It's the same at every single position, and that's just the vector 1, 2, because this has a coefficient of 1, 1i plus 2j is the 1, 2 vector. And now we're going to dot that with the dx, dy vector. But here's the thing, I have to specify boundaries for these because this is over a curve, but there are actually two things changing. There's an x component and a y component. So the x component, so we're going to write it like this, over the curve. And so if you dot these things together, you see that we have 1 dx plus 2 dy. I'm leaving a little bit of space here because the first component is going to get integrated with respect to x, and that should make sense because if this is in, for example, feet per second, and dx is a measure of, or not feet per second, but instead of feet per second, we'll say that's a force of newtons, let's say, and then these are measured in meters, then we have a product of newtons and meters, but we have to specify how many meters we move in the x direction. So x is going to go from, first of all, for the first component, x is going to go from x equals 1 to x equals 10. The 2 dy, that component, is going to go from y equals 10 to, or sorry, y equals 1 to y equals 10. Now along this curve, C1, notice that the only thing that's changing there is just the x value. The y value is remaining fixed. So in this first piece, we only need to compute the x change, and this second component we compute the y change. And you can kind of see that our angle between, vectors along our curve and the actual flow vectors, our angle is always between 0 and 90 degrees. So we should expect a net sum that is positive. And the integral of 1 dx is x evaluated at x equals 1 and x equals 10, plus the integral of 2 is 2y evaluated from y equals 1 to y equals 10. This is going to give me 10 minus 1 is 9, and add that to, 20 minus 2 is 18. So you see that we're going with the flow in both C1 and C2, in both of those curves, but we're going more with the flow along C2 because we get a larger dot product. You can actually see that that angle is a little bit smaller than the angles that we are having down here. And so we get a net line integral equal to 27. And so what would be the units of this? Well, if this were newtons and this were meters, this would be 27 joules of work. Now, because that's positive work, that means that the current is doing more work for us, and for the most part, because it's positive, we are going with the flow of current. Let's take a look at a physics application. So here we have a mass that's lying on a flat table attached to a spring whose other end is connected to the wall. The spring is extended 20 meters, so 20 meters beyond its rest position. Here's its rest position, so this is 20 meters, and released. If the axes are as shown in figure 18.6, when the spring is extended by a distance of x, the force exerted by the spring on the mass is given by, this is called Hooke's law, and this just means that if x is positive, the force will be negative. So if you pull a spring or a mass away from its rest point to the right, then if you let go of it, of course that mass would shoot towards the wall, and that's what this is indicating. K is some constant of proportionality that depends on the strength of the spring, and so that force is going to go in the opposite direction. Suppose the mass moves back to the rest position. How much work is done by the force exerted by the spring? So I know that to compute this, that this is a line integral, because it's the dot product of force and displacement. Along our oriented curve, it's the product of our vector field. And notice that this guy is only a function of x, but I'm going to write it as a function of our position vector, dotted with our displacement vector. And as we begin breaking this down, we see that our force function only has an I component, and that I component is negative k times x. K is just some constant. Now what about the y force? Well, there is no y force because this is only a horizontal spring. There is no up and down movement or up and down force in that assembly, therefore that force is 0. And once again, if we think about dr as dx and dy, then what we need to compute is accumulate the dot products along this path, negative kx dx plus 0 dy. So of course, in the y direction, there is no force, therefore that's not going to contribute to our line integral. And now we can break this up. We know that x is going to go from, we want to know how much work is done by the force exerted by the spring as the mass moves back to the rest position. So it has to go from a position of 20 units back to a position of 0 units. And so our lower bound on this integral is 20. Our upper bound is 0 because it's starting at 20 and moving back to 0. So this is going to be the integral from x equals 20 to x equals 0, negative kx dx. And when we integrate that, we're going to have negative k over 2 x squared evaluated from 20 to 0. Evaluate that at 0, you get 0 minus evaluate negative k over 2 x squared at 20, which is going to be times 400. And those negatives are going to cancel. 400 over 2 is 200, which is going to give me an overall force of 200k Newton meters or joules. Notice that this number is positive because back up here, k is a positive constant. So that means 200 is positive, k is positive. This is equal to a positive number. And what that means is that we're not doing any work, right? We're not pushing the mass. The mass is basically moving by virtue of the vector field. And since we're moving exactly in the direction of the vector field, we're not doing any work. All the work is being done by that vector field. Nice. So you can think about positive work as, in an intuitive sense, positive work makes you happy because somebody else is doing the work for you. Negative work is where you have to do a lot of the work, and so maybe you feel negative by the time you're done because you've done so much of it. Now, the velocity vector field for the Gulf Stream shows distinct eddies or regions where the water circulates. So we saw that Gulf Stream example. We can measure this circulation using a closed curve. That is, one that starts and ends at the same point. This is nothing different than what we explored, but if C is an oriented closed curve, the line integral of a vector field f around C is called the circulation of f around C. So all we mean by this is that if you have a vector field that, in here we have all of our vector field vectors, and if we were to take an oriented curve that somehow doesn't have to be a perfect circle, but let's say you took a path that looked like this along this closed curve. Notice that it's closed because it starts and stops at the same point. This is what's called a circulation. And just to emphasize to our reader that our line integral is along a circulation, notice how we just put this like O across the integral? That's the exact same thing as what we were describing up here, but for the person looking at this, this just says, oh, you want me to compute a line integral, but this line integral is over a circulation, so it must be a closed curve. Okay, so this is what we mean by closed curve, that basically you can continue writing around this circuit. There are other kinds of circulations. You can have rectangular circulations. You can have, of course, circular circulations. But these are all examples of closed curves. So here we're just going to look at these two figures and describe the sign of the circulation of the vector fields. This is the same idea as before, except all we're dealing with now is closed curves. So for example, C1, we see it's always going in the direction of the current because of the way it's oriented. It's oriented counterclockwise. The vector field is counterclockwise as well. That's positive work. That means we're going with the flow. So we would expect a net positive a net positive line integral, which is, again, just the sum of dot products. Now in this one, we're going around the circulation here. Here on this portion of C2, we are moving with the flow of current, so that's going to give us a positive dot product, positive dot product. Along here, we're moving perpendicular to, that means 90 degrees to the vectors, so here we're going to have 0 dot product. And same thing when we're going back this way, we're going perpendicular to the vectors, 0 dot product that way as well. Now because vertically, all these vectors are the same length, when I move back along this portion here, I can see that that is against 180 degrees to the current vector. And not only that, but since the vector is the same length, then this positive and this negative should cancel each other out, and I should end up with a zero network. So you can see here I went with the flow, so that was happy work, that was positive work, meaning the current was pushing me. Here the current wasn't really doing anything to me. I mean, it was pushing me to the right, but it wasn't preventing me from moving upwards. So that's no work at all, right? I wasn't doing any work, the current wasn't doing any work on me in the upward direction. But then I started going against the current, and now I had to really row super hard to get along that little piece of the oriented curve. So that cost me work. It undid the work that the current did for me down here. And then when I'm going, again, downwards, then I'm not affected by those vector fields in terms of the direction that I want to go in. And when I sum that together, I'm going to get a net zero. Now, everything is great with the process that we've explored for these line integrals, except that notice that our movements were always parallel to one of the axes. So in this curve, only the x component was changing, and in C2, only the y component was changing. Imagine that we actually wanted to go straight from 1, 1 to 10, 10. In other words, I wanted to cut across in this direction. It would be a lot harder to compute the line integral along that trajectory by using this path, because it would be a different path. Here only our x changes or only our y changes, and no two things change simultaneously. So the same thing goes here. Here we had a zero y component and no change in y, so these integrals worked out just fine. But a lot of times these shapes that take place in the vector field are parameterized. There is a parameterization like x equals cosine of t, y equals sine of t, that allows us to actually create this path in the vector field. So we want to ask ourselves, what if we have this curve which is actually your position is a function of time? That is, you press play and slowly that particle moves along that oriented curve, and you want to have that path be parameterized. So this is a more robust method. We're going to apply the exact same logic. We're just going to say that your initial position is actually your position at time 0, or t0, your initial time. This doesn't have to be time equals 0. This could be time 5, but t sub 0 just means your initial time. And then again, break up this curve into a series of intervals by equally spaced dots, in the sense that these are all the same amount of time has passed to get from one dot to the next. And so you can see that the delta Ri vector is the same thing. It's the difference between where you are here minus where you are here, and that will give us the displacement vector. So nothing has really changed in terms of the idea or the concept behind it, but we do have one little problem, and that is that when we were writing our line integrals earlier, we just said, position was a function of x and y, of where you are. But we now have, notice the difference here, we have that the position is now a function of time, that the value depends on t. And your position vector, recall, has your x position as a function of time, and your y position as a function of time. However, we cannot integrate dx and dy since x and y are both functions of another variable called t. So our issue here is that our integrand and our variables of integration are not both in terms of t. This, for like an oriented curve that is along a circle could be cosine t sine t. And when you multiply that dx dy, you'll get cosine t dx and sine t dy, but that's problematic because, well, this depends on t, but this is an integral with respect to x. So you can see the dilemma that we have here, but there is a little trick that we can perform. First, note that we have at each point in this parameterized path a position given by your position at time ti, where I represents the point number. The distance between any 2 points is the delta Ri, is your position where you are now minus where you were one time unit ago. And to get the dot product at any point, we multiply those two things together. We take the limit as delta Ri approaches 0. And here is one neat little trick to convert our dr vector into a dt vector. So recall that as delta Ri, that the length of that vector, as that approaches 0, this is going to be the integral over our curve from f of r of t dotted with our dr vector, which is dx and dy. Right, that's going to be our dr vector. But let's see if we can do some math on this guy. Delta Ri, well, that's the difference between 2 points. So here's an interesting thing. What if I did this? If I took delta Ri is equal to the position at time I plus 1 minus the position at time I, and if I divided this by the change in t, the change in delta t, which is ti plus 1 minus ti, multiplied by ti plus 1 minus ti. So notice here that what we've done is we've effectively multiplied by 1. We've divided by something, but we've also multiplied it by it. So this is still equal to our original expression. But notice that this is the difference quotient. So as delta r, the length of that thing approaches 0, it becomes, so let's see, the limit as the length of delta Ri approaches 0 of the delta Ri vector is the limit as this whole expression here approaches 0. Okay, multiplied by this thing here, which we're going to call delta t. That's just the change in time. And what we know is that if you take the limit as something approaches 0 of a difference quotient, or I'm sorry, in this case, the delta t approaches 0, because that's what's going to make our delta r vector smaller, is by making the time increments really small. As delta t, and we don't need the magnitude anymore because this is not a vector, this is just a scalar, time, as that approaches 0, well, this is going to approach the derivative of r, and delta t will approach dt. So what we've just established is that as we make delta Ri really small, this integral here will become the integral over the curve multiplied by the vector field of the vector field dotted with, well, now dr, which was, right, this is dr right here. What happens when delta Ri approaches 0, it becomes dr. And we just found out that dr can be replaced with, or is equal to, r prime of t times dt. So instead of using dr here, I could replace this with r prime of t times dt. And now my integral over the curve is really just my initial time and my final time. So at t equals a and at t equals b, those are the time spans that it takes for me to, say, get from p to q. If this was t equals 0 and this was t equals 5, then my limits would be from 0 to 5. And this is an incredibly useful formula to use. We had to do a mathematical trick here to try to get the dx dy into a dimension of time. But you'll see here that it's actually pretty straightforward to apply. The one challenge, though, of course, is that we have to actually find formulas for these parameterizations. So here we want to compute the amount of work done. We see that the vector field is x plus yi plus yj. So this is going to be x plus y and y for the second component. So that's my vector field. And then this curve is the quarter unit circle oriented counterclockwise as shown. So if I assume that this is t equals 0, that's t equals 0, and this over here is t equals pi halves, then I know that my x is going to equal cosine of t, and y is going to equal sine of t. That's just one parameterization of this circle, and of this quarter circle. You could have picked something like cosine 2t and sine 2t, but then it would have taken half the time to get to the point 0, 1. So you see that if I plug in 0 for time, x is equal to 1, y is equal to 0, and if I plug in pi halves for time, cosine of pi halves is 0, and sine of pi halves is 1. And so that's one way we could talk about this curve. So to compute the total work, I have to calculate from t equals 0 to t equals pi halves the force vector evaluated at my position. Okay, so I know I need everything in terms of t. X plus y simply won't do when I'm integrating dt, but I do know that x is equal to cosine of t, and I know that y is equal to sine of t. So if in my vector here I replace x with cosine of t, and I replace y with sine of t, so there's my y, there's my x. I'm going to add these two things together, and then now my second component of my force vector is simply the y value, which is sine of t. I now have my force vector converted to units of time. And the reason I can do that is because, yes, the size of your current vector depends on, or your force vector depends on where you are positionally, but your position depends on how much time has passed. So our vector here will be, cosine t sine t, sine of t, multiplied by the r prime vector. Okay, so the r prime vector, which is what we now need, is the derivative of the position. So if your position vector is this guy here, this is the position vector, then the derivative of your position vector, or your velocity vector, is going to be the derivative of cosine, which is negative sine, and the derivative of sine, which is cosine of t. And so once we have everything expressed in terms of t for our force vector, and we have r prime of t, this is going to be a dot product between these two things. So this is where we're going to get a scalar, and then integrate that dt. So this is what we call vector calculus. We're doing calculus on vectors. And the integral from t equals 0 to t equals pi halves, when we dot these together, we'll have cosine t times negative sine t, or negative cosine t times sine t. So that's just me multiplying this times this. And then distributing negative sine of t times sine t gives me negative sine squared t. Plus, now I have to add the product of these two together, which is cosine of t times sine of t. All of that with respect to t. With respect to t. But I see here, I get a little nicety, negative cosine t, positive cosine t cancel out. And so now I just have to compute the integral from 0 to pi halves of sine squared t, or negative sine squared t. And I can use Wolfram alpha to calculate that and get about 0.8 is our number of units of work. Now you can see that we're primarily going, that it's kind of hard to see here, but for the most part, oh, I'm sorry, this should be a negative because I forgot my negative sign. I was going to say, it seems like we're going against the current most of the time, so there should be a negative, and there should be a negative here as well. So you can see that in net we're going primarily against the flow of current, and so this is actually negative work, which means in order for me to row my boat through this stream, I have to pretty much go against the direction of current all the way along. So you can actually see here that like that vector there, that angle between the velocity and my actual position vector is greater than 90 degrees. Now the reason it's so small is because this is a unit circle and these values are all between -1 and 1, so we don't expect this to be too large. And so there we go. So that's our very first example working with it. Let's look at another one. Here we have a particle that's moving along the helix C given by this, and if you recall what this looks like, we have a particle basically moving along or over the z-axis. As time increases, this particle is going up, and it's moving counterclockwise. Let me actually just change my y and x so it looks like this. So x starts out 1, and then this particle is basically going to kind of circulate around here as it moves upwards. And it's subject to a force that's given by this really odd force. It's more than just gravity. It has a kind of a gravity component, but it also has some air resistance maybe, that what these two terms are. And so I want to calculate the total work done on this particle between those 2 points. So in order to do that, I have to, remember, I'm going to have to compute from t equals 0 to t equals 3 pi, the product between my vector field evaluated at my position multiplied by the derivative of the position vector. And the reason I know it's the derivative of it is because I'm parameterizing this curve. I'm not moving parallel to one of the axes. 99% of the time you're using this version of the formula. You're not using the original one because you're going to parameterize your paths. Okay, so I need 2 things here. The first thing is to calculate this, and to get that, all I need to do is, well, let's start with our position. We're going to need to know what our position is. Our position vector, r of t, is the vector cosine t, sine t, and 2t. So if I know that this is my x, my y, and my z, this is my x, that's my y of t, that's my z of t, then to get the force vector in terms of that, well, I see the force is equal to x of t, then the y component is equal to z of t, and the z component is equal to the product of x of t times the y of t. And so I need to get x, y, and z in terms of time. So for the top component, I'll plug in x of t, then z of t, and then the negative product between x and the z of t, which will give me 2t times cosine t. All right, so that's this thing here that we've just calculated is called f sub r of t, because it's our force evaluated at our current position, which is stated in terms of time. All of our position components are in terms of time. So that's what I'm going to put in for this guy here. Now I need the derivative of that position vector, which is r prime of t, and that's just going to be the derivative of all of my components of position. So the derivative of cosine is negative sine. Sine, its derivative is cosine, and derivative of 2t is 2. So when I calculate this dot product now, I have everything I need to get this. I just need to put the pieces together now. So this is going to be my integral from t equals 0 to t equals 3 pi of the dot product between this mess, cosine t, 2t, negative 2t times cosine t, dotted with my derivative of my position or my velocity vector, and that is taken dt. So this is going to be a real ugly looking thing, but we're not going to compute it by hand, so no worries there. So this is going to be, before you can type this into a calculator of some sort, you kind of need to write out the dot product, because unfortunately there's no vector integrator out there that I know of. So this will be negative cosine t times sine t plus 2t times cosine t, those are the y components, minus 4t cosine t dt. And now with Wolfram Alpha, you can calculate this. And we'll just leave it at that. You can now go type this in, and you should get a number. Okay, in this last example, I want to look at something where we have two different parameterizations for the exact same path. Consider the oriented path, which is a straight line segment running from 0, 0 to 1, 1. Calculate the line integral of the vector field 3x minus y and x along L using each of the parameterizations. So you can see that this guy here, when t is 0, will produce the ordered pair 0, 0. And the x and the y are always the same, which means we're moving along the line y equals x. Now at time 1, if we plug in the end boundary for this, well, t is 1, so that takes me to the point 1, 1. And that seems like the most intuitive way to get from 0, 0 to 1, 1. Look at the second parameterization. Here we're using exponential functions, yet when we plug in 0 for time, e to the t minus 1 is e to the 0, which is 1. 1 minus 1 is 0. Same thing for the second component. And when we plug in t equals ln of 2, well, the e to the ln of 2 is just 2. 2 minus 1 is 1. And so we get the point 1, 1. So both of these paths take me from 0, 0 to 1, 1, but they do it in different ways. And again, you notice that the x and the y components are always identical, which means we're traveling the line y equals x. And the y does equal the x, so that emphasizes it. For the first parameterization, if we compute the integral and the line integral, so for part A, from t equals 0 to t equals 1 of f evaluated at our position, r of t, multiplied by the derivative of the position vector. So I see that my force is the 3 times the x minus the y, and x and y are both t. So this is going to be the integral from t equals 0 to t equals 1 of, okay, again, I'm going to do 3x minus y. X is t. Y is t, so 3t minus t. The y component is simply just x, which is t, dotted with the derivative of the position vector. So this is our position vector, tt, and the derivative of t is 1, and the derivative of t is 1. And so that's the integral that I'm going to work through. So if I dot these together, I'll have the integral from t equals 0 to t equals 1. This is 2t times 1 plus t times 1, which is going to give me 3t with respect to t. And this is going to be the integral from t equals 0 to t equals, oh, sorry, I'm not going to do the integral. I'm going to compute the integral, rather. The integral of 3t is 3/2 t squared, evaluated from 0 to 1, which is just going to give me 1.5. So we're claiming that we're basically going with the current for the most part for this particular vector field. If I did it with method B, we're going to get the same answer. Or will we? Well, let's see. We know that at t equals 0, we'll be at the starting point, and at time ln2, we'll be at the point 1, 1. But in this case, I have to evaluate my vector field, which is 3x minus y. Well, x is e to the t minus 1. Y is 3 to the t minus 1. E to the t minus 1. And now for the y component of our vector field, that's just equal to the x function, which is e to the t minus 1. And then the derivative of my position vector is e to the t minus 1, e to the t minus 1, and the derivative of e to the t minus 1 is just e to the t dt. And this is going to be an uglier one to compute. And when I say ugly, I mean there's lots of exponentials floating around. But let's clean this up a bit. So here we'll have 3e to the t minus 3 minus e to the t plus 1. So 3e to the t minus e to the t will be 2e to the t. Negative 3 plus 1 will be negative 2. And then down here I'll have e to the t minus 1. And here I'll have e to the t and e to the t. So now I'm going to go ahead and dot them together. And so I will get the integral from t equals 0 to t equals ln2 of, when I multiply these two components, I'll have 2e to the 2t minus 2e to the t. And that's just the dot product of these two components. And now I'll have plus e to the 2t minus e to the t. And that's dt. So let's go ahead and compute this with Wolfram. And here it is, 1.5. And this is the same answer that we got earlier. And so the real conclusion here is there are infinitely many parameterizations for an oriented curve. The key is to set up the initial t and the final t to make sure you don't, quote, undershoot or overshoot your final destination.